Hi everyone, I thought I'd deal with a modeling problem in a video. This is the type of observation that one might get as a mathematical modeler. Some populations tend to have slow growth during autumn, and then the population actually declines, so that the number of the population actually goes down over winter, and then the population growth increases again over spring and summer. And we ask how this might be captured in a population model. So there's a few observations here, or there's a few things we need to note before we can start constructing our mathematical model. Populations tend to grow proportionate to themselves. So that is dp dt for p for population equals alpha p, right? And that actually has exponential or unbounded growth. Typically what bounds the growth is some sort of resource limitation. So a resource limitation is mostly a lack of food, sometimes it's a lack of space. In terms of plants, perhaps it's a lack of light. So what we say is that dp dt equals alpha p times some function of t and p, which describes the resource limit. So we can't simply just subtract members off the population. This won't be an additive term because you can't really, it makes no sense to keep reducing the population because the resources run out. So you want to change the rate at which the population grows. So what you might actually do is, if you're an applied scientist, you're going out and measuring populations, you're counting beetles or birds or fish, you might get data which is p as a function of time. Population over time. Right? Whatever that looks like, you can plot it and have a look and see what it does. Typically, you would see it grow, but you might see it grow at a non-uniform rate. Once you have p of t, even if it's numerical data, you can compute or estimate its derivative. Essentially, if you've got p data points, t p, you've got data points like, to make this a bit more interesting, you've got data points like that. To estimate the derivative, you compute the slope at each point, right? And you get MATLAB to do it, obviously, or some other numerical algorithm. So what you might go and do is you might go and plot all of these things, and you might plot, very importantly, this quantity. This is the relative growth in population. So the population growth divided by the total population at the time. Now this starts to look like a sensible function. This takes care of the fact that these things are getting bigger all the time. You're now looking at relative contributions. So for example, this might look like time dp dt 1 on p summer, autumn, winter, spring. So let's say you've got 1 year's worth of data. You might see quite high population growth in summer, declining as you come into autumn, gets worse, sort of bottoms out around winter. Towards the end of winter, things start to look good again. Right, and by springtime, you're back up roughly to the same level as you were in summer. So what you might be inspired to do is approximate this data curve by some mathematical function which fits. All right, so you've got all these data points. You want a nice mathematical function that will work. So you really need 2 parameters. You need A, and you need some sort of like time shift or phase that we'll call phi. Right, and then you might fit, say, just a cosine function of time. Oh, and you need a frequency. That's actually more like a wavelength than a phase. The phase goes from some sort of 0 point to a maximum. So you would have cos, some sort of frequency or wavelength parameter, plus this phase shift and an amplitude. So what you've ended up with from your data, or from simply our hypothesis at the moment, we haven't actually got any data. This data is just fake and illustrative. We've ended up with this model. Cosine. So different phases. I'll draw a different phase here. I'll draw it degrees out of phase. So this is our so now we have a population model that accounts for seasonal variation in the relative growth rate. So there we have it.